Hi. Hi. Fine, thanks. You?
Again, pass this over to you, or do you want to have it when you start? Or do you
No, it's okay. That's what it is. I'm sure.
get it started?
Okay. So that, so that you record
It's already recorded.
Okay, okay.
The files are so small, so it's a big,
It's not a big deal.
you can chop off whatever you don't need to keep it covering all the bases.
Then you have to merge the video and the audio.
Yes.
Okay.
But there's always a marker on the video,
Mhm.
which gives me a signal.
Okay.
Then I know it, that's why I clap.
I see.
Signal, so I match the video to the audio.
Okay, okay. They say you should run just after 9:30.
Oh, they said that. Well, when is the,
Like half an hour.
yeah, let's do a quick check. Because the food was pretty badass.
What documents? Maybe wait until it's marked.
Yeah, the next one. They're just,
Oh, there's just confusion. There's no reason going to.
sorry, he's right.
I think we'll wait another 5 minutes.
Sure.
I don't know what it means. They said it you just have to manage.
The important thing is that they were not intoxicated.
No, only the.
So they are healthy, that's important. Then I will hear.
There is a big protest on the highway.
Okay.
In Johannesburg.
Close.
So they closed down the highway.
Probably.
So they
They
don't
diverted to small roads.
from another road.
What are they doing? It's the release of the leader of this, for the political figure from the fight against apartheid. Was murdered
Yeah, 30 years ago.
and the guy who murdered him is now getting free.
That's why they
That's why they protest.
So he was in prison for life, but, life.
Life changes.
You can get parole after some years.
Yeah.
I've been asking for parole for like 20 years now, we've never given it.
So they were actually free.
But yeah, some court decided that.
Well, that's some court, usually because of the
The constitutional court, the court decided that you cannot anymore. After 20 years.
How old is he?
Yeah.
He was a apparently earlier this week he was suspended by
Yeah.
but he's right. So they're not too many people are.
It's not very popular.
No, some ultra right-wing nationalists.
And then whether like countries have on the war.
Basically, always managed to destroy everything in democracy.
the guy you murdered.
Ah, okay, okay. Okay.
So after Mandela possibly. The popular guy was
One of the communist stuff.
which was on the shoe.
Okay.
So the protests on the highway,
Yeah,
just like today.
Wait, this like this block? Which one is it?
Yeah. Yeah, that's what
I thought at the base to get
So it's easier to come So me, so efficient with WWE is it was certainly.
should be my microphone here. What are the rules to do this? Yeah.
There are some small rooms next to the hallway that you could go without waiting for it, but obviously when this happens, you know, or you can do like sampling, which is go to the airport, and then the airport.
Oh, so that's not.
So that's not so sometimes that's, we have to wait us to do that, and take small rooms.
I was just thinking because my channel is at 11.
Have you heard of it? Have you heard of it? Or is it me that will do? No, have you heard of it?
I think so. I'm not sure that you just
I'm not
it's
sure what is the latest.
They're on the central, so they're not gonna, maybe.
Yeah, no, but, it's good if you got information for,
So you use it hard to.
Yes, I got it.
from them.
Yeah.
So you're going to use material.
For them.
So how long will it take?
No, let's start, it will take them at least 20 minutes.
Okay, okay,
So.
okay. Is it recording? Okay.
Okay, well, welcome everybody to the fourth day of the 12th Joburg School, with the continuation of Mario's lectures on Supersymmetry.
Okay, thank you. Thank you very much. So let's continue our discussion about supergravities, standard supergravities, and in particular gauge supergravities. Today we are going to start discussing about gauge supergravities, so the gauging procedure. But let me first recap what we have learned so far about extended supergravities. Okay, let me list the main points, which it's important to bear in mind because we will need them when discussing the gauging and the gauging procedure. Okay, so and extended the dimensional supras first scalar fields which are related or connected to p-forms through supersymmetry. Are non-minimally coupled to them. What does non-minimally coupled mean? Means that they are coupled through their kinetic terms. This coupling is encoded, so it's non-minimal. Okay? Couplings are encoded in a matrix, symmetric matrix, defined over on the scalar manifold. Scalars, I recall, are coordinates on this internal manifold, okay, which is a Riemannian manifold. 2. The definition of this matrix and its transformation property with respect to what we call G, that is the isometry group of the scalar manifold, is built in the geometry of the scalar manifold. The geometric structures defined on the scalar manifold. So it's built in. It means that it is fixed. It is fixed by supersymmetry, because supersymmetry fixes the coupling, okay, of scalars to the p-forms, and it's fixed up to an initial choice of basis for the p-forms and for this matrix here. 3. Push this up and this down. Push this down. 3. These mathematical structures allows to extend the action of G to the p-forms, in particular to their free space, okay, through a matrix representation of G, which we call R, which is an homomorphism between G and automorphism on the vector space of the p-forms. That is matrices, constant matrices, which we denoted by R here G and R matrices. And N being their indices. What do they act on? They act on a vector of field strengths, K form field strengths, where K is equal to T plus 1, okay? Transforming them into F prime n K, which is equal to R of G, the minus 1, and M F K N. Okay, this is the transformation. This is the action. This matrix defines the action on covariant vectors. This is the typical way a contravariant vector transforms under this group G. Okay, what is this Fm? Fm K is just the vector of field strengths. K from field strengths if D is different from 2K. While if D is equal to 2K, okay, Fm is equal to the vector of electric field strengths, so field strengths and their magnetic duals. Therefore, in this case, the action of the group, the global symmetry group G, okay, can be viewed as a generalized electric magnetic action, transforming or combining electric fields with their magnetic fields. This is a generalization of the U1 duality of Maxwell equations. Okay. Now, thanks to this extension, okay, of action of G on P forms, okay, and as we shall see also on fermion fields, G is promoted to a global symmetry group of the theory. Okay, so this extended action, this combined action on scalar fields, P forms, and fermion fields, we shall see in a moment how fermion fields transform, okay, promote this group G, the isometry group of the scalar manifold, to global symmetry of the entire theory, from global symmetry of the scalar field Lagrangian, okay, as an isometry, to global symmetry group of the entire theory. The matrix M transforms in this way. Okay, so these are the main results we obtained yesterday. Okay, so G global symmetry of the theory. Okay? Yes.
The group of the SLPZ duality of Maxwell theory at global symmetry. What would you call them?
The SL2C.
Sorry, electric magnetic duality.
Right. Oh, no, I know. In the presence of electric and magnetic charges, that is SL2C. Now, in the absence of charges, that is a U1 symmetry, right? The usual Maxwell equations are invariant under the U1 symmetry, which transform F and star F, right, into cosine theta, sin theta, minus sin theta, cosine.
Okay, so
Now, if you consider Yang-Mills theory with their couplings, okay, you define a complexified constant, okay, then you can you generalize this duality to an SL2 duality, okay, because it also acts on the coupling constant, that is on this complexified coupling constant. Now we will show how this group G generalizes precisely this action on the complexified coupling constant. The group G in 4 dimensions precisely generalizes this action. Okay, but in the absence of electric magnetic charges, okay, ordinary Maxwell theory that has this U1 duality symmetry. It's important to emphasize that the duality symmetry G in supergravity is in general non-compact. So it's a non-compact generalization. An example, SL2, in that case. But this generalizes this, the action on the complexified coupling constant. We also found that, okay, there were two cases. Yeah. Yeah.
The idea of global symmetries. There's this spoke theorem, I suppose, that says that there shouldn't be global symmetries in theories of gravity, quantum gravity. What's your take on it? Is this
So here we are considering classical theories. Okay, so in classical theories, we do have global symmetries. Okay, I showed how to construct it, and they are continuous, described by continuous figures. Okay, what happens is that when you go quantum, okay, when you introduce quantum corrections, when you quantize charges, that's required, you know, then this group is broken to a suitable discrete subgroup. Okay, so you do have discrete global symmetries. An example is type 2D superstring theory global symmetries. An example is type 2D superstring theory. Type 2D superstring theory does have a global symmetry group, which is SL2Z, right? That's the S duality group, right? Yeah. So I think the statement has to do with continuous global symmetries, and at the quantum level there are no continuous global symmetries. Okay.
So,
Yeah.
that's more of the semantic discussion perhaps, but I was thinking of the global symmetry is that something that doesn't change the theory at all. Whereas duality, you know, it changes the coupling. I know that's ultimately the physics is the same.
Yeah.
But it seems to be a different theory.
I totally agree with you. But so far we are discussing ungauged probability, so there are no couplings. There are, you see, what you would call coupling constant in ordinary super Young theory now are described by dynamical fields, which are scalar fields. So the transformation property of, say, the complexified coupling constant here is viewed as the effect of an isometry on the scalar manifold, which is SL2 over SO2. Okay, so SL2 over SO2 in the simple case of a complexified coupling constant of super Young theory. So in this case, the SL2 action on this complexified coupling constant, okay, is not viewed as an action on non-dynamical objects, coupling constant, because now these coupling constants are dynamical because they are scalar fields of the theory. So that's really a global symmetry, a true global symmetry, because you're transforming only elementary fields of your theory. There are no coupling constants at this stage. Today we are going to introduce coupling constants. So we are going to introduce non-dynamic objects, constants that can be grouped in a non-dynamic object called the embedding tensor. And in that case, what you're saying applies to that case, because then everything is formally can be written formally in a G-covariant way. However, provided we transform also this ionic object, that is this non-dynamical object. But this means that we are really doing an equivalence between two different theories with different coupling constants. Okay, but so far there are no coupling constants, no masses, no net. Everything is expressed in terms of dynamical field transforming under G. So G is really a global symmetry. Okay. So this is in U1 in case of Maxwell theory. So for V equal to 2k, we also distinguished two cases. Okay, one in which k is odd, and then R of G, P of G, G is contained in SP to NP. R is symplectic. Okay? Now, vectors in a four-dimensional supergravity, they fall in this class. Okay? So this case. K even. R P of G is containing O and P, comma and P. Example, D equals 6, 2 4s in D equals 6. Or, okay, D equal 8, 4 forms equal 4 equal 8 is still in this case. Yes, because K is equal to solve also. Okay, so this is the these are the main points that we discussed last time. Okay. Another point, let me add another point, and then we focus on four-dimensional fields. Okay. So we go to point 4. Okay. For supergravities in equal 4 and greater than 2, or in general number of supercharges greater than 8, the scalar manifold is homogeneous, symmetric. This means that it is a coset manifold, G over H is related to it being homogeneous, where G now is a semi-simple equilibrium, and H is maximal compact subgroup. Okay. G being semi-simple is related to the fact that the manifold is symmetric. Okay. That follows from the definition of symmetric manifolds, because semi-simple algebra, they have an automorphism, which is an involutive automorphism, which is the Cartan involution. And that is a feature of semi-simple algebras. This Cartan involution acts as a reflection symmetry on the tangent space. And the existence of this reflection isometry is a feature of symmetric manifold. So this reflection isometry, which is in the definition of symmetric manifold, follows from the existence of semi-simple algebras of a Cartan involution. Okay. In these cases, the matrix M is constructed easily. So let's denote by G the algebra of G, the algebra generating G. Okay. There is an involution on G, which is an involutive automorphism identity, which is called the Cartan involution. It determines the splitting of G into the algebra generating its maximal compact subgroup, that is its maximal compact subalgebra, and a space K. K is the eigenspace of sigma corresponding to eigenvalues minus 2. This is nothing but the reflection I was talking about before, and H eigenspace plus 1. Okay? In a suitable basis, matrix representation, in a suitable basis of any matrix representation. Sigma on an element, a representation of the algebra, okay, is equal to minus n diagonal. So you see that H are compact, that is, have imaginary eigenvalues. The elements of K have real eigenvalues. In a suitable basis, K are Hermitian, H anti-Hermitian. But this we can always do for semi-simple reactors. Hermitian, anti-Hermitian. Okay. An example is SL2. We were talking about before. Consider G equals SL2. The group of 2 by 2 invertible matrices with unit determinant. Okay, is its algebra, which I denote by SL2R. Okay, what are the generators? Well, we have seen applications of this or examples of this in the other lectures. The generators can be chosen to be I sigma 1, and sigma 2. Okay? These are the Pauli matrices. These are the Pauli matrices. H is I sigma 2. It's generated by I sigma 2, which is the only, you see, compact matrix here. Imagine eigenvalues. These are all real, or Hermitian. K sigma 1, sigma 2. Okay. Okay, so how do you construct a matrix M in these models? Well, you can take a coset representative in G over H. You can choose coset representative as you want. Okay. It depends on how many parameters. Well, the least number of parameters that allow you to move from one point, which I call the origin, to any other point, which I call P. The least number of parameters. As we know, H is the invariance of the point, of any point. Okay, well, H is the invariance of the origin, then any point have equivalent stabilizers. Okay, which are all equivalent to one another. H is called the isotropic group. H is called the isotropic group. So H contains all the parameters which are totally ineffective for moving from one point to any other. So how many parameters does a coset representative depend on? What are this least number of independent parameters that allow you to reach any point from a given point? Clearly, they are the total number of parameters, which is the dimension G, minus the number of parameters which are unaffected, namely the number of parameters in H. Number of scalar fields is equal to the dimension of G over H, and this is equal to the dimension of G minus the dimension of H. For any G in G, how do isometries act on the coset representative? Well, if I take any G in G, okay, it will take me from a point P to a point P prime. The fact that it is homogeneous means that given any couple of points, there exists an isometry connecting them. If I act by means of G on L of P, the representative, coset representative P, I land in the coset of P prime. Okay? But in general, not in the same coset representative. Not in our coset representative in P prime. So what I know that this is in the coset of P prime. But this means that G times L of P is equal to L of P prime times H, a transformation in the isomorphic group, in the isotropy group, sorry, which depends on G and on P. So choosing a coset representative amounts to choosing the representation of the manifold. Sorry, a parametrization of the manifold in terms of scale. And this choice is not unique. There are different choices one can make. This is the action, general action of an isometry on the coset representative. Now, bosonic fields transform directly under G. Fermionic fields transform under this compensating transformation. So, for any G in G, and for any phi points in the scalar manifold, the fermions transform in the fermion prime, which is equal to H of G phi acting on the fermions. And this is the transformation property under fermions. Fermions transform under the compensating transformation. Remember what we said in the first lecture. Fermions always transform under the action of the symmetry group of the point. So, when we talk about space-time, it transforms under the local Lorentz transformation, which is a symmetry point of space-time. With respect to transformation on the scalar manifold, they transform under the symmetry of the point in the scalar manifold, which is H. Okay? Yeah.
So by this equation, the main equation, when lower left, lower and right. So global isometry group action fixed by the local isometry group.
Sorry, which one?
Yeah.
This one. Yeah.
The definition is global.
This is global.
Yeah.
Okay. This is local. Local in the scalar manifold, not in space-time. So be careful. These are always global transformations with respect to space-time. So they depend on space-time, but the scalar fields, like a Kähler transformation. An example of these are Kähler transformations on Kähler manifolds. Kähler transformations are defined by functions on the Kähler manifolds, that is, functions on the complex coordinates, but they don't depend explicitly on space-time. This is important. Okay? Invariance means that under this, which is required, is that the theory cannot depend on how we choose the field line on the scalar manifold. And invariance under local Lorentz on space-time means that the theory cannot depend on how we choose the theta or field line basis on space-time. Okay? The theory cannot depend on that. And this is the invariance. Okay? So this is global with respect to space-time. Otherwise, this invariance would imply a reduction of degrees of freedom. If it were local with respect to space-time, okay? It implies that the effective number of propagating degrees of freedom is less than the one which is described by the theory. Okay?
But the statement is the same as the fermion statement of times and space, of the times and spatial points.
Yes.
Is that the same statement?
The same. There are now two tangent spaces.
Yeah.
But it's the same statement. It's the same statement. So we have two manifolds, space-time and scalar manifold. Space-time and scalar manifold. Here the symmetry of the point is local Lorentz, O 1D minus 1 of P, okay, of X. Here, scalar fields define a point on this manifold, okay? And here the symmetry group is H of phi, okay? Fermions transform under this and under this. They transform under the symmetry of the point. What does the symmetry of the point act on? It acts on the basis of vectors on the vector of the tangent space for a fixed point. So they just change the basis of vectors of the tangent space. And this is telling us that the theory cannot depend on our choice of the basis of vectors on the tangent space. Okay?
But I guess among other things that tells us that the scalar manifold goes to the spin. We have to allow spinners.
Oh,
Or
no, you don't need this representation. Need not be spinorial representation. This has to be spinorial representation. This is generally not. It could be any one.
The scalar in the scalar manifold, or have any representation?
No, the representation is fixed by the theory. So it's fixed by supersymmetry. For instance, in n equal 1 theories, okay, in n equal 1 theories, scalar fields are related to enter the chiral multiplex together with spin 1/2 fields. Okay. Now, supersymmetry fixes the coupling of scalars to fields spin 1/2 through a structure on this manifold, which is a Hodge bundle, U1 bundle, that tells you how spinors should transform under Kähler transformations. If you do a Kähler transformation on the Kähler manifold, which is an invariance of the matrix, okay, it depends on the point, the fermion field should transform in a well-defined way through a U1 transformation. And this is fixed by this bundle structure. Okay, so they are a section of a U1 bundle in that case, and that is an example. Okay, so always, that's a general rule. Supersymmetry fixes structure on the scalar manifold, which fixes up to some residual freedom the coupling of the scalar fields to the other fields that are related to scalar fields by supersymmetry. Could be fermion fields, Hodge-Kähler manifold, or p-folds, and this is the kind of bundles we're talking about now. Okay. So in these cases in which the scalar manifold is homogeneous symmetric, well, the matrix M is really defined. M of phi is equal to RP of L of phi times sigma L minus 1 of phi. And this is a matrix. Okay? You can easily see that this does not depend on our choice of the cosette representative. And if you move from M phi prime through an isometry, you use this transformation property of the cosette representative. And you see that this gives you RP of G times M of phi times RP of G transpose. Okay? Careful, when you do this, you have to use the fact that L phi times sigma L minus 1, L phi prime times sigma L minus 1 phi prime. This is equal, let's use this equation here, which defines the action of the isometry on L. This is equal to G times L of phi times H minus 1 times sigma times, I have to do this one. Okay, this is, let me write it correctly. Yeah, okay, then now use this, that sigma is an homomorphism, sorry, is an homomorphism, so in particular is an homomorphism of groups, and sigma of H is equal to H. So that H cancels out, and this is G times L of phi times sigma L minus 1 of phi times sigma G minus 1. Okay? Then you apply Rp, which is a homomorphism, and you use the fact that in a suitable representation, Rp of sigma G minus 1 is equal to Rp of G transpose in a suitable basis. Real basis. Okay? These are all real representations. So you use these properties, and then you see that a matrix M defined like this has the correct transformation property. Okay? Okay. For n equal to 2 models in 4 dimensions, things is more complicated because scalar manifolds may be homogeneous, non-symmetric, or not homogeneous at all. But in this case, on these manifolds, okay, a flat is defined, which takes care of this, and in particular implies the definition of the matrix M, which and its correct transformation property under isometry transformation. Okay. This has to do, well, this structure is not defined over the whole scalar manifold, okay, but just over the part of the scalar manifold, which is parameterized by scalar fields lying in the same supermultiplets as vector fields. Scalar fields. Scalar fields. In vector multiplets. Can be a vector multiplex is defined by a vector, two spinors, and a complex scalar, A running from 1 to 2, because we have two supersymmetries. This is a vector multiplex. You can have a number of them, so I, and in this case, the scalar fields, they group in complex coordinates, which I denote by Zi and Z bar I. The scalar manifold is a scalar manifold. Sorry, the scalar manifold spanned by these scalars is a scalar manifold. In this case. What does scalar manifold means that there exists a coordinate basis on which the matrix has just these components, Gi, J bar. And these components can be written as the derivative with respect to Zi, derivative with respect to Z bar, J bar of a scalar potential. Of a scalar potential, 2 dots here. Okay? Clearly, The scalar potential is not uniquely defined because I can change the definition of chi by k by the sum of a normomorphic function and an anti-holomorphic one. Okay, and this is called the scalar transformation. And the scalar, the matrix, you see, these cancel out here, so the matrix simply does not change. Okay, these are scalar transformations. So on top of this scalar manifold, okay, which the condition that the manifold be scalar is there also for n equal to 1, as we said before. Okay. On top of it, there is what we call Hodge structure, which fixes the coupling of the scalar to the vector to the spin 1/2 fields. That fixes the coupling of the scalar fields to the fermions, which are basically psi, k, e, and lambda, call it I, collective symbol for the fermions, spin 1/2, spin 2/2. Hot scalar takes care of this, and is implied by supersymmetry. Hot scalar takes care of this, and is implied by supersymmetry. And that implies that, in particular, under scalar transformations, fermionic fields should transform by a U1 transformation, a suitable U1 transformation. You see, symmetry of the point. This is a U1 transformation. Similarly, lambda I has to transform with e to the minus I over 2 independent of lambda I. Okay, this is implied by this structure. There's a Hodge scalar structure. This is a fiber bundle. This is the statement that the fermions should transform as a section of this fiber bundle. Okay, but I won't go into further details about this. On top of this, in n equal to 2 theories, so this is there also for n equal 1, because scalars are connected to spin 1/2 fields also in n equal 1. So also in n equal 1, n equal 1 theories, the scalar manifold is a Hodge scalar. So it's not a genetic scalar manifold. The scalar manifold with this additional structure, which fixes the coupling, which in this case is minimal coupling of the fermion fields and the scalar fields, and tell you how fermions should transform under a scalar transformation. You see, they transform under U1, which is the symmetry of the point. That what belongs to is part of the symmetry of the point. But in n equal to 2 theories, we have something more. We have the coupling of these scalar fields which lie in the vector multiplets to the vector fields. So we have another structure. Okay. We have a flat symplectic bundle. This means that F, M, nu are transformed as a section of this bundle, and the matrix M as a matrix on the fiber. So even if in this case the manifold may not be homogeneous, this structure takes care of everything. defines an M, which transforms, as we said before, under transformation in geometry group, which are, in this case, are the defines our structure group transformations on. Okay, so this is the general structure in any project. Are there questions? Yes.
Under the transformation of the fermions, under the Taylor transformation of the functions that the exponent both the homomorphic part or the anti-homomorphic?
Both. Because you see, imaginary part of F is equal to 1 over 2i times f of z minus f of z bar. So you see, this is a U1 bundle, so it transforms under both f and f bar. So it transforms under a U1 transformation, because this is a phase. So this is a U1 transformation. And it's part of the symmetry group. So the general rule is that fermion fields transform always under the symmetry group of the point. And this is part of the symmetry group of the point. Okay? So a Hodge-Taylor manifold with this flat symmetric bundle is called the spatial Taylor manifold. Okay, so in n equal 1 we have just Hodge-Taylor manifolds. In n equals 2 we have special Taylor manifold because we need an extra structure to define the coupling of these scalar fields to the vector fields, which are encoded in this matrix M. And this matrix M has to transform correspondingly as a matrix on the fiber. Okay? I cannot go further on the in discussing this mathematical structure. Okay, I should speed up a bit. So, in what happens in what follows, I will focus on four-dimensional fields, extended supergravities. Okay. So D equal 4 and greater or equal to supergravities. Okay. So in this case, L bosonic is minus so it's square root of G times minus Ricci scalar over 2. I'm setting the 8 pi G kappa is equal to 8 pi Gn equal to 1 plus 1/2 G Rs phi d mu phi r d mu by s plus I lambda sigma. I remember the general form that I wrote last time. Okay, F lambda mu F sigma mu. Okay, plus R lambda sigma phi F lambda mu star F sigma mu. Can there be a potential, a scalar potential? No, that cannot be, because as we said, in order to introduce a scalar potential, without manifestly breaking the symmetry, we need to apply the gauging procedure. So we need to introduce some local symmetry, internal symmetry, gauged by the vector. That's the only way for these theories to introduce a non-trivial dynamics among the scalar fields. Okay. So in this case, we define G lambda as minus F8 mu as minus F to the mu rho sigma, just as we did before. We described last time. Okay, and we define a symplectic vector of field strengths. F lambda mu and G lambda mu. Okay, we define also the matrix M in terms of these matrices I and R. Remember that positivity domain for the kinetic terms of the vector fields require I, which is symmetric, to be negative definite, and R, well, but that's just the way for to be negative definite, and R, well, but that's just the way for the way it enters here is a symmetric matrix. So there's no positivity restriction on R. Okay. Okay. So this case, this can be written in this very compact form. Okay. So 1, 0, minus R, 1 times I minus 1, 0, 0, times 1 minus R, 0, 1. Now, minus R, 0, 1. You just compute the products. Okay. This is the general definition of M and N in terms of these two matrices. We have so don't mistake this I for an identity. No, it's not. It's not a highly non-trivial, non-linear matrix in this case. Okay. There's also a symplectic representation of the isometry group, which acts as we said. That acts as a generalized electromagnetic transformation. That's why the group G is also called the duality group. Okay? And everything can be written in a manifest invariant way. And RG, R1 of G, can be written in a block structure. Let me yes. Can be written as D minus C minus B A. Okay. Well, this is just a definition, okay, of various blocks. This is each is 2 and 1 number of vectors, 2 and 1. Duality transformation. The transformation of the matrix through which the field strengths transform is this transpose, which is A, B, C. Okay, so it's like this. This is a symplectic transformation. So this means that R1 G transpose times C times R1 of G is equal to C. So it leaves this matrix C invariant. C is equal to 0, 1, minus 1. Okay? It leaves. There's a minus here because we are P is equal to 1. We gave this general structure yesterday. Now we are specializing this 4 dimensions. Okay? This is the way it transforms. So you immediately see from here that R1 of G minus 1 transpose is equal to minus C R of G times C. Okay, just check. This is true. So from this matrix, I can obtain this matrix by simply doing minus C times the matrix. Okay, this is the property. I need a few things before starting to discuss the gauging. I will focus on four-dimensional views. Okay. Okay. So how does the field strength transform? Well, F going to F prime equals RG, R1G minus 1 transpose times F, which is AB, CD times F and G. That's the way it works. Okay. F transforms with the strange matrix because it's a contravariant vector. So it transforms with the transformation R with minus 1 transpose. That's the way contravariant vector transforms is R of G is defined as an action on covariant. Okay. So you see that F prime lambda is equal to A lambda sigma F sigma plus B lambda sigma G sigma. A and B are constant matrices. Remember, these are constant. These are flat symplectic bound. Flat symplectic bound means that the transition functions, which in this case are these matrices, are constant. This is the way the field strength transforms. Okay? So this is the new field strength, the gravity transform field strength. You see, it's a combination of dual field strengths, electric field strength, and their magnetic duals. As we said before, the Bianchi identity on the new vector fields, on the new vector field strengths, are satisfied if B is different from 0, require V G sigma equals 0, which are field equations. So the Bianchi identities for the new field strengths require if G is different from 0, the field equations in the old in the previous frame. Okay. So this is if B is different from 0, this is a non-shell because it requires field equations. This is a non-shell global symmetry. It's a non-shell global symmetry because it requires the field equations. If B is different from 0. Okay. Those transformations defined by B equals 0 define a subgroup of G such that G R1 of G is equal to D minus C 0 A. Okay. In this case, you can easily verify that A minus 1 is equal to B transpose, and also A times C is equal to A times C transpose. This is a check this. That the symplectic condition that the matrix is symplectic in this case implies that A minus 1 D transpose and A times C is a symmetric matrix. Okay. You see B is equal to 0. This implies that F lambda goes into an F prime lambda, which only depends on the electric field strength in the previous frame. So we have a linear action. of GE on F. This is an optional symmetry. Because the Bianchi identities which are required for the correct definition of the new vector fields, the duality protected vector fields, are implied by the Bianchi identities of the space. So this is a non-shared symmetry, that is symmetry of the action. So while G is always the same, and that's the symmetry, global symmetry of the field equations and Bianchi identities, the symmetry of the action, the global symmetry of the action, is defined by this smaller, okay? If we change the symplectic frame, okay, that is, we change what we call electric and magnetic. So we change the basis. Symplectic basis. For Fn. Where this is a symplectic matrix. If we change the symplectic frame, we make a different choice. We call electric and one we call magnetic. G doesn't change. So this is an ambiguity in the definition, in the description of the engaged theory. G, the global symmetry of the theory, does not change. The action changes. L goes into an L prime. The action changes because you're changing the basis. So the embedding of G, capital G, in the symplectic group changes. So changes the group whose matrices are represented in this way. That is the global symmetry group of the latter. Okay. Now, when we're going to gauge the model, okay, we'll have to choose a suitable subgroup of the symmetry, global symmetry group of the action. So starting from different symplectic frames, we have different choices because our group, our gauge group should be contained in GE. Okay? So symplectic frames, changing symplectic frame not change the physics of the model. It's just a field redefinition on the equation of motion. It's not a symmetry in general. It's not a symmetry. It's a symmetry only if E is in G. It's not a symmetry. It's just a field redefinition. It does not change the physics. However, it changes the Lagrangian description. These two Lagrangians are not related by local field redefinition. So they are unequivalent. Okay. Good. One last thing. Then I promise to come. Now we know how M transforms under this transformation. It transforms like a matrix. M phi goes into M phi prime, which is R1 of G times M of phi times R1 of G transpose. Okay, this is how the matrix M always. Now we are interested in the transformation properties of the two matrices I and R, which define the non-minimal coupling of the scalar fields to the vector fields. How do I and R transform? Okay. Write R1 of G as we did before in block notation as D minus C minus B A. Okay, and this is symplectic. we can define M a complex matrix, which is equal to R lambda sigma plus I lambda sigma. This is what we call R and I, because I is the imaginary part of a complex matrix, and R is the real part of the same complex matrix. That's the reason why. And that goes into n prime, which is equal to C plus Dn times A plus Bn transpose. Okay? Minus 1. Minus. So you see, it transforms like this. From this, it is easy to find the transformation property of R and I. Notice the similarity between this transformation property and that of the complexified structure constant. In a Yang-Mills theory, we find tau, which is theta over 2 pi plus 4 pi I over E squared. Okay? Theta is the theta term, this is the complement. And this transforms in tau prime, which is equal to C plus D tau times A plus B and the minus square, where A, B, C, D are in SE2 in this case, which is SL. You notice the similarity. So this matrix M, complex matrix M, generalizes the complexified coupling constant. R generalizes the theta term, and I generalizes the inverse square coupling. However, sorry, it's a leftover. Okay, cool. Thanks. And you see they transform in the same way, basically in the same way, though with respect to different groups. Okay. Okay. So, but in a Yang-Mills theory, theta and E are parameters. This is the main part. Here, R and I are not parameters; they are function scales, and this is induced by a transformation on the scale. So this is an important point. So G is really a global symmetry of the theory. Okay, then if we quantize electric and magnetic charges, so we go quantum, what happens is that G breaks into quantum. You see that the group G acts as an electric magnetic duality transformation, so it acts on electric and magnetic charges. So when charges are quantized, this action should preserve the charge lattice. This breaks G into G of Z, which is G intersected with SP 2n1, Z. So the global symmetry group now is discrete. Okay, no matter charges now. Okay, is discrete, and it was conjectured by Hull and Townsend. Conjectured by Hull and Townsend back in 1994, if I'm not wrong. 1994. That this group encodes as part of the known ST and U dualities. Yeah, 94. G, Z encodes string and dualities. This is another reason why it's called duality. Okay. Okay, how much time do we have for this morning? This first hour?
Well, we're over by about 10 minutes.
Okay. We'll stop here. It's good time to stop. Now I reach.
Engaging next.
Now we will stop engaging. Yeah.
Okay, great, thanks. And we can have coffee maybe for about 20 minutes until.
Okay.
11:40.
Okay. Thank you. Thank you very much.
So at this stage, the screen doesn't go to we don't put it in
Well, it's the global, but it's not continuous. So we don't have
The word I worry is Robert's got an even discrete global symmetry flat in one of them.
But then, I mean, how do you want how do you deal with the S equal to the
But this sounds.
Because
Because at this stage, once you.
Because S equal to yes.
You find that the community not local.
Yes.
You can't base it more just the single program.
Of course. So, but these charges, so the charges in this and these together is a charges that the silicon example. So basically, there are charges entering, for example, or they're like coordination. Okay, like right and part of the have charges for it, but these charges are not about the integral of but all in this case, these charges are solution charges. This means that they are actual theories of all fields are connected. So they don't have so these are really meaningful, but this does not show the problem.
That's not what's okay, for the global situations.
For the global symmetry, no, because the global symmetry acts on these by transforming it. It has an action, and through this action we can
Then this transformation might get you out of the ground, and then you might say, well, that's not serious. But that's maybe a bit of a narrow.
But this is if these charges were in the ground. As we will see in the case we will get that charges in the ground. And we are going to calculate the ground in such a way that everything is collided. But there is a trick. Because very these charges okay, they are always always. So this one is of the right.
Then there's something still here.
So what you're saying is true. If they were not mutually local, then that would be a problem for them. But these are always mutually local. This is important. Okay.
I talked to you
But
about
this is ideally, it's like a reason to for example. That is
But the question, yeah, I guess the question is
Yeah.
what characterizes exactly.
I think the global symmetry is a continuous. That is continuous global symmetry because that is associated with the network charge.
Right.
So those symmetries which are associated with network charges, these are ruled out because there was an argument that I can. But since this is discrete, it's no longer generators, decimal generators, and so no more network charges. But I would be interested to see the precise. Because this wasn't an observation that
sorry. Should be dance. Sorry. Should be dance. I haven't read this in wrong schedule.
there is a short.
There's a short version, but it's not comprehensible.
Not comprehensive, but this is the
Yes.
comprehensible one.
This is comprehensible, which is very long.
That's
And,
from the abstract.
We first showed that any global symmetry is clear continuous in the bulk one theory, the CFD dual between symmetry and CFD. And thus there are no bulk global symmetry being in CFD.
But you know, well, global symmetries in the SAT.
Continuous.
But we need SAT. Okay, we don't even have a yes. No, I agree with that. But here we don't have a yes because there's no potential. So that is, I agree.
But I think they want to.
He went into this claim for quantum gravity more generally, so Harlan has another paper, where
But then if you do it is 5 times 5, it's still yes of 2.
Yeah.
Which is the SL2 symmetry on the end. And that is
But what
symmetry.
is something done, yes, it's not a symmetry.
No,
Well, that's what I'm getting the confusion.
I agree, it's not
maybe the
symmetry.
definition is symmetry, but they have this other paper, although William, where they make stages needed to add maybe a CFD.
Beyond this, it's okay. Sure, maybe, yeah, thanks. Because I always thought that the thing was really, they also went.
What's your email?
My email is mario.brillante@gmail.com.
million project, but they don't pay for it. What kind of sucks.
They get me heat.
Let us know how this kind of hard. We have another kind of it's kind of soft, and it's kind of light brown. And that's easier.
Okay. Yeah. I don't know, I guess it kind of makes sense considering the versions yeah.
So it's a different region, so this comes from north. So he means that the Olympics are in the north part, but there are more central parts and there are different. But this is more typical, this is what you buy, and the supermarkets can buy it.
Could be a big church.
Yeah, the whole market is pretty.
Okay. No problem. No. Okay, you just give me a sign. Shall I start? Okay, so using this expression, this formula, you see how R and I transform. Okay, now important thing is to see how they transform under an electric. Electric means an off-shell global symmetry. That is a global symmetry represented by this block matrix with the B equals 0. This is a global symmetry of the action. No? It's important to see how R and I transform under symmetry G. And you see, if you just use this formula, you can deduce the corresponding transformation property of the blocks I and R. This is G in GE. Okay? And you see they transform like this. Now, interestingly, you see that R transforms covariantly, now, through block T, but it also has a shift. This is a constant shift. Okay? So this constant shift determines a variation of the Lagrangian, so it's not true that the Lagrangian is invariant. The Lagrangian varies, but varies by this term here. This term is a total derivative because C and A are constant blocks. So this is a total derivative, so it won't affect the equations of motion. Okay. However, it will affect path integral. So the quantum theory, because the action varies at the exponent by a total derivative. Okay. However, so by boundary term. However, we know that at the quantum level, C and A are quantized. So this is really, thanks to this term here amounts to an invariance of the quantum theories, yeah, so of the path integral in general, since C and A are quantized. Transformations in which C is different from 0 are called Peccei-Quinn transformations. So transformations which imply this characteristic shift in R, they are called Peccei-Quinn transformations. Peccei-Quinn. And they are implied by or associated with shift symmetry in axionic fields. Okay. Okay. Are there any questions? Not? We move to gauging. Discuss gauging. So the gauging procedure. We start from an ungauged supergravity, the form of the kind we have been discussing so far, with a certain amount of supersymmetry, a certain field content, so supermultiplied content, and we perform the gauging, which consists in promote a suitable subgroup of the global symmetry group of the Lagrangian to local symmetry gauged by the vector fields. Okay? This requires introducing minimal couplings, covariant derivatives, non-abelian field strengths. Okay?
Sure. When you say we start with certain field content,
Yes.
certain number of multiplets, does it completely specify the starting point, or you can have the same number of multiplets but different spaces and all that.
Yeah, you choose, one of the starting point is the engaged supergravity. You choose any engaged supergravity you want. Okay, we're considering extended models. So this means that you can really consider any 4 dimensions model with n greater or equal than 2. Any. Okay, that will be defined by a certain amount of supersymmetry and a certain field content in this sense.
Yeah, but they don't specify, well, I guess, the scalars can live on different scalar manifolds.
No. The scalars will live on the same scalar manifold. So once you fix the engaged supergravity, you're fixing the supersymmetry is fixing everything, including if you're talking about field content and scalars, okay, you're also specifying the scalar manifold.
Because I can think of different homogeneous spaces that say the same dimension.
Yes,
So,
yes,
but
yes.
they're different.
No, I totally agree with you. I totally agree with you. In n equal to 2, then in n equal to 2, you have the freedom to choose different with the same dimensions, so the same amount of scalar fields, so same field content, but you can choose different geometries for the scalar metric in n equal to 2 models. So there you have this freedom. For n greater than 2, n equal 3, 4, and so on, once you fix the field content, so the super multiplet structure, the super multiplets, then the scalar manifold is fixed for n greater than 3. For n equal to 2, greater or equal than 3. For n equal to 2, you have also to specify at the beginning, choose a scalar manifold. Yeah. And that is important. So that is one of the starting data. Yeah, thank you. So second, well, when you introduce minimal couplings, you're breaking supersymmetry. When you're introducing the minimal coupling that you need to make this group a local symmetry, you're breaking supersymmetry explicitly. So the rest of the gauging procedure consists in modifying the Lagrangian L and the Fermi-Susy transformation properties in order to restore the original amount of supersymmetry of the gauge theory we started. Okay, and this implies masses, general Yukawa terms, and a scalar potential. Okay, so our approach to the gauging procedure, okay, is going to be gradual in the sense that I think it's more instructive to discuss the gauging procedure in a non-G covariant form, okay? Because in that case, doing this, you better understand the origin of the various constraints on the gauging, okay? That is on the embedding tensor, as we shall see. And then move to the duality covariant formulation of the gauging procedure, which will call for the so-called hierarchy, tensor hierarchy. Okay, good. So we start from an engaged theory. In D equal 4, we're focusing on 4-dimensional theory and greater or equal than 2. In a certain symplectic frame, we shall label the components of this symplectic frame by a Hafted index because we want to distinguish this symplectic frame from a generic. The vector fields are labeled by a Hafted index. Okay, so we're going to have M hat, which is F lambda hat and G lambda hat. Okay? And then duality group X one as we know. Okay? Then we take, so this is the original symplectic frame, which we're going to call electric symplectic frame. Okay, this is our starting point. So we fix an ungauged supergravity, meaning that for any, we are also fixing the geometry of the scale. We're making a choice. Okay. Next. In this symplectic frame, the global symmetry will have a certain embedding inside the symplectic group. So in particular, R1 of GE will consist of matrices of the form A D minus C A 0, the 0 here. Okay? It consists of matrices of this form. Symplectic matrices. Next, we choose G inside GE, global symmetry group of the Lagrange. And we want to promote it, promote A, so promote to local symmetry. How would we do this in a non-supersymmetric theory? Well, if we have a non-supersymmetric theory, say a theory describing a complex scalar, okay, with a certain global symmetry, like you want global symmetry on the complex scalar, okay? Then what would we do for gauging, in order to gauge this symmetry? We would introduce a vector field or a number of vector fields in general, if the group is non-abelian, okay? We would introduce vector fields, transforming it in the coadjoint representation of the gauge group. So we would introduce a lambda mu in the coadjoint representation of this global, this G, the would-be gauge group, okay? Introduce minimal couplings, that is covariant derivatives, gauge covariant derivatives. Minimal couplings, that is covariant derivatives, gauge covariant derivatives. Define non-abelian of these strengths, okay? And then make the theory in this way invariant under local symmetries G, okay? This is what we would do in a non-supersymmetric theory. We just add vector fields with a specific transformation property with respect to G. The vector fields that we need, the gauge fields, we just add them together with their kinetic term, and the theory becomes locally invariant. In supergravity, we're not completely free to do this. Why? Because we are starting from a theory, an engaged theory of a theory. We are starting from an engaged theory in which the field content is fixed. So we can only use the vector fields that are there in the engaged theory. We cannot introduce vector fields with certain transformation properties. No. We must use the vector fields that we have in our engaged theory. First. Second, all bosonic fields in the engaged theory. Second, all bosonic fields in the engaged theory have a well-defined transformation property under the global symmetry group G, and therefore also under GE. And therefore also the vector fields have a well-defined transformation property under the group GE, and therefore under any subgroup of GE. Okay? So we are not completely free or at least not as free as if we would be in a non-supersymmetric theory. Because we have to start from a well-defined theory. So, actions of any subgroup of GE on a lambda mu is fixed as a global symmetry. As global symmetry, that is fixed. Let's describe the action of an infinitesimal transformation. Let us denote by x lambda the gauge generators. The gauge generators. Okay? You see, they have a lower lambda, while A have another lambda x. So that G is equal to x of a generic combination lambda and a hat of x lambda or cycle inside. Okay? So the infinitesimal generators of the gauge group will be denoted by x lambda, lower lambda. Okay? So what is their block structure? Well, these are in GE, so their block structure is that one. R1 of x lambda, R1 of x lambda, they're going to have a 0 here because they are generators in G. Then they have a block here. This block is x lambda sigma gamma. Okay? A block here is x lambda sigma gamma, and a block here which is x lambda sigma pi, let's call it pi, delta pi. Okay? All hatted indices. So this is the block structure, general block structure of a generator in the gauge group that we want to. That's the most general form. So the infinitesimal duality action of the would-be gauge group on the vector fields x and their magnetic field. Okay? Where? Notice that being a G in G, the B block is 0. So this means that the block with this index structure is 0. It has to be a global symmetry of the action. Okay? Good. And then these generators are symplectic. They are symplectic generators. What does it mean? C plus C times R1 x lambda is equal to 0. So this is the symplectic condition on the generators. Before we wrote symplectic condition on finite transformations. This is the symplectic condition on infinitesimal generators. Now you substitute here the general form, and what you end up with is the condition that x lambda sigma gamma is equal to minus x lambda gamma sigma with a minus sign. This is related to the condition that we wrote before, A equal to D, A transpose equal to D minus 1. Remember, for finite transformation. Then we also have the condition that x lambda sigma gamma is symmetric in the last indices. Okay, so this comes from the condition that this transformation has to be symplectic. Okay, namely it has to generate a symplectic transformation. Right? Okay, now remember how the field strengths transform under transformation in GE. They transform, the electric field strengths at least, transform linearly. F prime is equal to RG, remember, 1 minus 1 transpose F. Okay? And then we saw that F prime lambda was equal to A lambda sigma F sigma. Was a linear. This is what we saw for finite transformation. Finite. This is what we saw for finite transformation. How about infinitesimal transformations? Okay. Delta F prime lambda is equal to, let us consider a transformation generated by a certain parameter psi. Okay. This psi, let's use the hat for the indices because we are in the electric range. So a psi gamma times x gamma lambda sigma f. This is the way it transforms under an infinitesimal. Finite transformation, infinitesimal transformation. This is also equal to minus psi gamma x gamma sigma lambda f sigma half. Okay? This is how it transforms. I'm not going to gauging yet. This is how it transforms in the ungauged theory by a global transformation in G, in the would-be gauge. So our vector fields do have a well-defined transformation property under any subgroup of GE that we choose. They already have this transformation property. We cannot invent it. Okay. So the same transformation property holds for the vector fields. Okay. Delta A mu lambda is equal to minus psi gamma gamma x gamma sigma lambda A mu sigma. Okay, this is the way it takes linear transformation. Now we want A lambda should transform in the co-adjoint representation of G, because we want to promote the use these vector fields as gauge vectors. And gauge vectors should transform in the quadrant representation of the gauge. Otherwise, nothing works. Okay. So, x lambda, x sigma, our gauge generators, they close a inside big G with these structure constants. They close another structure constants satisfy the Jacobi by consistency. Jacobi. So A transforms in the joint. This implies that delta A, this is psi, okay, mu lambda should be equal to psi gamma f gamma sigma lambda A sigma. So saying that it transforms in the cojoint means that it transforms to the structure constants of the gauge. This is the same. Let's compare these two. They should hold for any A and for any psi. So this implies that x lambda sigma gamma. I avoid putting the brackets. Okay, they are understood. X lambda sigma gamma. I avoid putting the brackets. Okay, they are understood. This is equal to minus f lambda sigma gamma. So this condition doesn't work for any subgroups G of the global symmetry group of the Lagrange. No, this poses a constraint on the possible choices of our gauge group. Only for those whose action, duality action on the electric field strength is related to the structure constant in this way, only those are eligible as gauge groups. The others are not. But this is, you see, a constraint, a quadratic constraint on possible choices, on the parameters which define the possible choices of G, of the algebra, of the gauge algebra and the global symmetry algebra. X lambda, x sigma, is equal to minus x lambda sigma, gamma, x gamma. Then we have also that x lambda sigma, sorry, the symmetric part of x lambda sigma, gamma has to be zero because they have to act as structure constants. So they must be antisymmetric in the first place. Okay? This is a constraint. This is a constraint on those parameters which define the possible choices of our gauge algebra and the global symmetry algebra. Parameters that we will encode in an embedding tensor. Okay? Of course, X should also satisfy the Jacobi. Okay. Good. So we see our choice is not totally free. Okay, we are constrained in our choice of the possible gauge. Another constraint on the possible choices of the gauge group which is, well, we have used it implicitly. We have used it implicitly, clearly. Dimension of G. The dimension of G must be less or equal than the number of vector fields that we have at our disposal. This is a trigger one. We have used it implicitly. Okay, we can all just use the vector field that we have at our disposal. But now, among all these transformations, we also have those transformations which with an off-diagonal block, the C block that we considered before. So if we take RV or X lambda, okay, in the form X lambda sigma gamma, X lambda sigma gamma, X lambda gamma sigma 0, okay, we can also have transformations in which this block is not zero. The so-called Peccei transformations, infinitesimal Peccei transformations. Under this transformation, remember the formula we wrote before for the transformation property of the blocks R and I. Okay? You see that delta R lambda sigma. If we apply this transformation properties formula here to an infinitesimal transformation, we can easily find 2 psi delta times x delta lambda gamma r sigma gamma symmetrized lambda sigma. Okay. This is just applying the transformation of this infinitesimal. Plus minus psi lambda delta x delta lambda transformation. Written in an infinitesimal form. Now we saw how the Lagrangian transforms under this transformation. It transforms by a total derivative. L4 goes into left right. Delta L4 is equal to minus psi delta, psi delta x delta lambda sigma f lambda wedge f sigma. Okay. Now this is a total derivative. Only this side is constant. But now we want to promote this group to a global, from local global symmetry group of the Lagrangian local symmetry. We would like to make its parameters local. That is space-time dependence. G local. This implies psi lambda equal to psi lambda of x, mu. Now, if psi depends on x, this is no longer a symmetry. So how can we cope with that? The answer was given, and I'm not going to rederive it. The answer was given by David, Lauwers, and Van Rooyen. And they showed that in order to cancel this term, you have to add a topological term to the Lagrange, depending on this, precisely on this x. So you have to add a term like minus g. G is going to be our coupling constant divided by r divided by 3 x lambda sigma gamma a lambda wedge a sigma wedge d a gamma plus 3 over 8 g x delta pi gamma a delta wedge a There is a 3. There is a 3. Okay? So they showed that you can cancel. So they showed that you can cancel this term, which is not a global, but it's not a derivative now. You can cancel by a variation of this term. Provided x lambda sigma gamma equal to 0. Provided this is true. So this mechanism works provided you impose this condition. So this is one of the conditions that we have for biaggregation that we have to add on. So within the group of constraints that we have on the possible choices of the behavior. This is one.
But is this term supersymmetric by itself, or do you need to add the fermions
You need to add the fermions.
of this term?
But they all. No. There's no particular fermion term for this term. So the fermion terms, and they're not related specifically to this or that term. Okay, they are Yukawa terms. So they have a very general form. However, they are the tensors defining these Yukawa terms, called the masters of the fermion fields, depend also on this. So the variation of this will produce a term which is going to be cancelled by the variation of the Yukawa term to first order engine.
So you need to modify the Yukawa term.
Yeah, but everything is going to be encoded in the definition of the matrices, the mass matrices entering the Yukawa terms, which are depending on the scalar fields. So they are mass matrices only in a vacuum. Okay, otherwise it's Yukawa terms. Okay, but these matrices depend also on this. So if you want the dependence of these matrices on this is precisely needed for the cancellation of supersymmetry variation.
Small t, there is a gauge.
It's a gauge coupling constant.
So that you take that to 0, and then you go back to the global.
You go back, yeah. So it's important to define a g, so that if you switch it off, so to set it to 0, you're back to the ungauged.
And then also those what they call extra terms of your coupling will also go to 0.
It will also go to 0. Your coupling will be order g. And then you need also order g squared term in the Lagrange, which is a potential, the scalar potential, and that's all. So, but now I'm going to discuss this: how you modify the Lagrange in order to restore supersymmetry.
What did you assume that it's only a single gauge group? You cannot have a product gauge group for
You can.
Then you want to have a G1 and G2 group?
You can definitely. Yeah. This is just an overall. This is just an overall one. Just a convenient parameter to define the. This is just an overall one. Just a convenient parameter to define the limit in which the theory is engaged. Okay, but as we shall see, the gauge parameters are in this x. So this x, these blocks, will in general depend on other parameters. So in general, will depend on. You can have an algebra which is the direct sum of 2 or 3 or more algebras. Okay. So G, if you want, is the overall coupling constant. If you have more of them, overall one. Setting that to 0 will mean setting the whole gauge to 0. Okay, so let us recall all the constraints that we have found. Okay, and then we proceed in with the gauging procedure. That is, we proceed making the Lagrangian locally invariant under transformation in this group G. So the constraints of G. We have found a set of constraints. Some are linear, and they are x, lambda, sigma, gamma, that's 0. X lambda sigma gamma is equal to minus x lambda gamma sigma. And then we also have x lambda sigma gamma is equal to 0. Okay, these are the constraints we worked out so far. And lambda sigma gamma equals 0. This is the last constraint condition that we found for the cancellation of the shape of E. These are the linear ones. Then we also have a quadratic. Okay, quadratic constraint. Quadratic because you see it's quadratic in the matrix elements of length. Okay. Okay. Now, how do we make a group a local symmetry group? We introduce a connection, a gauge connection. We introduce a gauge connection. We introduce a gauge connection. Let's denote this gauge connection by omega mu. This is a, as usual, connection must have a space-time index, okay, because it's a connection. And it has to have values in the gauge algebra. So this is going to be G, because this is our overall coupling law, times A lambda of X mu. These are the vector fields that we have in our theory, times X lambda. Okay, this is the gauge function. The vector fields gauging the generators of G. Okay, now we define also a field strength. Two form, which is F. Well, let's write it as 2 form, which is equal to 1 of G. It's defined as 1 of G. G omega minus omega wedge omega. Okay. This is standard in HTTPs. Okay. This is how you define F and the covariant derivative. The covariant derivative on a field phi, which is in a certain representation of the gauge group, which I call R, is equal to d phi minus omega, so R of omega on. So if phi transforms in a certain representation R, whatever, of our gauge group and so of our gauge algebra, this is the standard definition of a covariant derivative. Exercise that I give you is the following. Take a transformation U in G. Show that D is covariant if and only if omega transforms under U in an omega prime, which is U omega U minus 1 minus U d U minus 1. Check. check that this is the correct transformation property of a gauge connection in order for the covariant derivative defined in this way to be covariant. Okay? Okay. Here it is. Here you go. Other exercise. Check that the field strength 2 form, which is, you see, a 2 form with values in the algebra, has the correct transformation property, namely that F goes into under U, F prime, which is U F. That's the correct transformation property. So that I advise you to check. Okay. Another identity property that you should check is the following. It's called the Ricci. Property that you should check is the following. It's called the Ricci identity. But for a gauge group, generic gauge group, d squared 5, this is equal to minus g r of f 5. Check. Okay. And then the antident. Which is df, defined as df, minus omega f plus f omega, which is df, defined as df, minus omega f plus f omega is equal to, this is the definition. Okay? This is the Bianchi identity. That you should also check. Okay. And then, well, let's the field strength in components along a basis of the other. So, F, let's write F as F lambda X lambda. So let's expand now these two forms which has values in the algebra on a basis of the algebra. Okay? See that F lambda is equal to D A lambda plus G X sigma gamma lambda A sigma wedge A lambda gamma, sorry, divided by 2. Check. And finally, from this transformation property and the definition of omega here, under an infinitesimal transformation, u of x, which is the identity, plus g epsilon lambda x lambda. So under an infinitesimal transformation, epsilon, depending on space-time, but much less than 1, very small, you verify that delta E is equal to d covariant derivative of epsilon lambda, which is equal to d epsilon lambda plus d A sigma x sigma gamma lambda times epsilon gamma. Also this advisory to check. Okay, this variation of A as can be derived from here, the infinitesimal variation, is just the covariant derivative of the of epsilon. Okay. Okay. So this is the harmonic we to perform the gating. Then we perform the gating. Two. We replace ordinary derivatives by H covariant derivatives. And abelian field strengths by non-abelian field strengths. Okay. What you end up with is engaged. The engaged theory will become a gauged Lagrangian LG, which is locally J variant. Here, because we are written it in terms of quantities which are manifestly covariant with respect to the gauging. So you do this in your ungauged Lagrangian replace, in these replacements. This in your ungauged Lagrangian replace, in these replacements. You also have to add that term. Okay? So you also have to add the David Flowers one week. So add also the David Flowers 1 week. And then you will end up with a gauge Lagrangian, which is manifestly invariant. Okay? By construction. However, this is not supersymmetric. Supersymmetry is broken. How do we restore supersymmetry? Well, we proceed through a method which is basically the Noether method. Namely, we iteratively modify the Lagrangian and the supersymmetry transformation properties of the Fermion fields iteratively in the powers of G until we end up with a supersymmetric action. We have restored the original supersymmetry of the engaged theory. To do that, and that is the third point. This is the most interesting point because the scalar potential and mass terms will enter the game. The orders plus delta L G1 terms of order G plus delta L terms of order G squared. And we have to introduce also additional terms in the supersymmetry transformation properties of the terminal fields. Let us denote the fermion fields by psi A mu. These are the gravity expresses. Sorry.
So LG0, is that the gauge by anti-symmetry?
Precisely. This one.
And then what is delta on the higher terms?
I'm going to write them down now. Yeah. These are the terms that you have to write, and they have a universal form. Once you fix the gauge, fix G, choose the gauge. They are totally fixed. So these are our gravity suppressed spinorial index. And these are the spin 1/2. I is the index labeling generically all these spin 1/2. Some of these may be part of the gravitational supermultiplet, and they are called dilatini. Others of the vector multiplets, they are called gaugini. Others of the hypermultiplets, when there are hypermultiplets, that is equal to called hyperini. I denote them collectively by lambda line. Here's the general expression of that energy. 1 is proportional to G. Twice psi bar A mu gamma mu psi E mu S A B plus I lambda bar I gamma mu psi A and IA plus lambda bar I lambda J and IJ plus Hermitian quantity. Because these are complex. Okay, but the Lagrangian has to be real. So you have to add these terms. They are Hermitian conjugates. You see, first observation, this is first order in G. Second observation, it depends on these tensors, M, N, and psi. I'm going to tell you more about them. For the time being, we just say that these tensors also enter the supersymmetry variation, that is the first two, of the permanent psi delta supersymmetry psi A mu. This is D mu epsilon A plus IG SAB gamma mu epsilon A. Here I'm using the Weyl basis for the spin. This means that gamma phi epsilon A psi A lambda I is equal to plus epsilon A psi. So with lower indices plus chirality, upper index minus chirality. This is useful because in this basis the R symmetry is manifest. Okay, delta epsilon lambda I is equal to blah 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 terms that are there also in the engaged theory. Okay, not writing them. Plus G, this is the additional term that you have to write. And IA epsilon A. Okay, IA epsilon A. Okay. So you see, you have to add terms to the supersymmetry variation of the fermionic fields. These terms depend precisely on the same matrices that define the Yukawa terms. These are Yukawa terms. Why are they Yukawa terms? Because the matrices A, B depend on phi, and I, A depend on phi. M, I, J depend on phi. So these terms are coupling, Yukawa couplings between these main tensors, which depend on phi, so scalar fields, and fermionians. These are called Yukawa. Okay? So you need to add them. Yes?
First of all, it is 20 past, so maybe
Okay,
the
okay.
next 10 minutes is a natural place to.
Sure. Thank you. I will go. Yeah.
But also, so I think of Yukawas typically as terms of 5 side bar.
Yes.
But these are functional phi.
These are functions of phi in general. They are highly nonlinear functions of phi.
But I guess it's still called Yukawa.
This is called, yeah, because it's just phi times psi psi. So it's basically higher order in the scalar fields. But yeah, I would call them Yukawa. Yeah, although they are clear generalization of the original Yukawa. Right? So these tensors depend on phi and on the gauge group. Okay? Okay, that's not the end of the story, because we need to add also another term, which is second order in the coupling constant. In the gauge coupling. So delta LG2, this is a potential, a scalar potential. Well, which depends on x, on phi, and on the gauge. Okay? Then times okay. I guess there is also a sort of the also here, because we are always so times is okay. Now the scalar potential is totally fixed in terms of these tensors here. So once you choose the gauging, all these tensors, which are called Fermion shift tensors, are fixed. And the scalar potential is fixed. The scalar potential has to satisfy this identity. This comes from the requirement that all the G-squared terms in the supersymmetry variation of the Lagrange cancel out. So supersymmetry invariance of the Lagrange implies this identity, G-squared times n bar I n ij minus 12 s b s bar b c s c a. One condition here is that SAB immediately follows from the way letters Lagrange is symmetric. Okay? So this is called the potential word identity. Potential word identity. So all these are implied by supersymmetry. If we do these transformations, so if we do these transformations in the Lagrangian, we add these terms to order G and G squared, then the Lagrangian, the gauge Lagrangian, is going to preserve the same amount of supersymmetry as the original. Okay, where these tensors here are constructed in a well-defined way from gauge to gauge generators. Okay, I'm going to show how they are constructed when we are going to introduce generators. Okay, so one last thing is I haven't discussed the minimal couplings to the fermionic field. Okay, but you can define a gauge connection, gauging only the part of the gauge group which is in the isotropic group H, and because the fermions only field cup. Okay, so you can define like that and define covariant derivatives also for the fermions. One last comment, and then we stop for today. Is notice the analogy between this construction and the theory n equal 1 equal 4 pure supergravity with cosmological constants constructed by Townsend that we discussed in the very first lecture. Notice the similarity. There, in order to introduce a cosmological constant, which plays the role there of a potential, we didn't have scalar fields, so the cosmological constant was a trivial potential. Okay, we needed to add mass term for the fermion fields and an additional term to the supersymmetry transformation of psi. So in that case, A and B run from 1 to 1 because it's n equal 1. So in that case, it was very simple. Can I delete this? So in the case of n equal 1 equal 4 with lambda equal 0, okay, then in that case it was just 1, basically. S11 was lambda over 2, and V, the scalar potential, which was lambda, was just minus 3 lambda squared. Clearly, there were no spin 1/2 fields, so n was equal to 0, or the rest is equal to 0. You can easily verify that these satisfy the word identity. So it is instructive to verify word identity in that simple case. Okay. How much time do we have now?
It's a good place to stop.
Okay, sure.
Maybe just one question.
Sure.
So what term that we finish at order G squared, that we're going to have higher terms? Maybe you said it, but
Yeah, no, I mean, these Noether procedure, they typically stop at one stage, so they converge. Direct construction, you prove it by direct
so
construction.
there's no philosophical argument. I mean,
No.
you just have to do computation.
Not that I know. You do the computation and you verify that the things cancel out. You know, that is enough for things to work. So like another procedure, they stop at some stage.
But it could have been 2 orders higher, principle.
In principle, yes. In principle,
So
yes.
how-
But the structure of supergravity is such that
Yeah.
that's at the second order. I don't know of a philosophical reason, deep reason for that.
Okay, great. Are there any further questions? Okay, well, let's thank Mario for the lecture.
Thank you very much.
And lunch is the usual place. People can get there. I'll let you know when we come back.